Hey, all right. My name's Bryan, and this is part one of our three-part series on creating custom PCBs. And pretty stoked to show you how easy it is to design PCBs and assemble them at home. There's three steps to creating a PCB. The first is to create a schematic, which is the drawing version, the layout of the logical layout of components and whatnot. It's called, also known as schematic capture. And the second piece of this is to actually lay out the physical PCB, so doing PCB layout. And then the third part will cover actually getting them fabricated, getting a custom PCB fabricated, and then assembling them. And we're gonna cover how to easily assemble these at home, and hopefully demystify the whole process here. Now, in this series of talks, we're going to create a Meadow Core-Compute module powered CO2 sensor board. So this is going to be something super simple. We're going to use Meadow add-on modules to just build a simple board that has a CO2 sensor on it and is core compute powered. It'll also have an RGB LED. And like I mentioned, the whole point of this is to really show just how easy it is to do this, at a home lab, and how really accessible this has become over the years. Really, what's happened is that in the last, 5-10 years, the PCB tool supply chain and modern EDA tools, that is. PCB design tools have really become very accessible, and PCBs themselves are very affordable to make, and they're a lot easier than actually sometimes breadboarding, or as you can see here, this is an early prototype of something I made a while back, and it took a long time to assemble this, and ultimately, it's not necessarily very reliable to breadboard things. Oftentimes you're like debugging things and it's just, there's a loose wire or something. And PCBs are one of those things that are necessary anyway for going to production. So the earlier you start in on them, oftentimes, honestly, the easier it is to build IoT. And I also think that they wind up, making a much cleaner project. And even though you have to wait for PCB to be fabricated and shipped back to you, I actually think that it's ultimately faster than trying to hand assemble prototypes. So for that reason, generally for prototypes, once I'm moving past just a project lab with stuff built in, I tend to go to a PCB design process and begin that, because it really it's just like better all around. And there's a lot of tools today to help you build PCB, to design PCBs. One incredibly popular one is Eagle. Eagle used to be open source and free, but it was purchased by Autodesk, and it's not so much anymore. Today we're going to use Easy EDA, which is another free, easy to use tool. And I like Easy EDA because it's got very little ramp up time in terms of like the learning curve, and it basically does everything that I need it to do. There's another one that's becoming pretty popular called Flux, and super powerful tool, also free, and has a lot of great collaboration tools and AI to actually help you know if your design's correct and whatnot. But I don't really love the UX, the actual designer on it, which is unfortunate because their back end, their supply chain management and things like that is really good. Also, KiCad is another one that is very popular. It's open source and community supported, and that's actually what we use internally for our Meadow boards. Again, I tend to use Easy EDA just because it is a lot easier to get started with, and I think that the UX is a lot cleaner. But again, KiCad's a great one, and then Upverter's another one that is fairly popular. Recently, it was purchased by Altium, and there's also a number of like less accessible EDA tools. Probably the best one out there is Altium, but it's incredibly expensive. And then there's other, Cadence makes one and stuff. But I would, if you're new to PCB design, I would start with one of these. And what we're going to cover today is pretty universal to any of these, any app. Just, it doesn't really matter which one you choose. What we'll learn today is pretty universal to all of them. So without further ado, why don't we get to it? So like I said, we're going to make this Core-Compute powered CO2 sensor. So I'm going to come into Easy EDA, and first thing that I'm going to do is, let's see here, switch over to that. Okay, so here I am in Easy EDA, and just a real quick introduction to the user interface. Over here on the left bar is where your projects are, and then there's we'll come back to the design manager later. Common library is where you'll find common components, resistors, capacitors, and stuff. And library is where you'll actually go and search for more complex components, and we'll get into that in a moment. And this is your edit area here in the center, and then you've got properties on the right. So pretty standard application. So we're going to start in here. We're going to do new project, and I'm going to say Dev Camp 2023, and this is going to be my CO2 sensor. So that will create a new schematic design, and here it is. Here's the project, and you can see here's the schematic, and I'm just going to rename this schematic. And while I'm here, I'm going to do some setup. Core-Compute, call it CCM CO2 sensor. This is going to be my first revision. Wilderness Labs. All right, here we go. So, the first thing that I want to do here is that, because this is a Core-Compute powered design, I'm going to start dropping in my main components, and I'm going to start kind of with the main stuff first. So I'm going to go to library, and this is where I find, like this is the large library of components. And in here you can search for symbol or footprint. Symbol is what you have in your schematic drawing, and footprint is actually what goes on your PCB, and that's where the solder footprint. And then these classes are different kind of places or sources for parts. So if I search for Meadow, you see that there's workspace, which are the ones I've created. LCSC are sort of official LCSC parts, and LCSC is it's like the DigiKey of Asia. And then system are built-in stuff. So if I wanted like a resistor, the system ones will have the system group stuff will show up in there. The common stuff that's like in the common library here. And then user contributed is as it sounds. These are folks in the community, and really when you're looking for parts in here, the ones that come from the system or LCSC are generally pretty reliable. I would say they're high quality footprints and symbols, generally about 99% accurate. You still want to check out the footprint and make sure that it's correct for your part. And when you're doing user contributed stuff, you have to be a little bit more vigilant around making sure that the parts are correct, etc. Now here I am gonna grab this Meadow F7 V2 Core-Compute module, and this is the logical version of it, and I'll show you as we place this. So here's the symbol, and here's a footprint preview. So I place this, and it's the logical layout because you'll notice that these pins are not in order. They're really broken out into their logical sort of grouping. And all right, so I've got that. And then the next thing that I want to do is basically every core compute design is going to need a USB interface for deploying and debugging applications, and it's going to need a boot and a reset pin. And so what we've done is we've created these add-on modules to make designing a lot easier. So this is especially true for when you're prototyping PCBs. We solved a bunch of sort of common use cases and put them in these add-on modules. And we talked about this earlier or yesterday in the keynote. But these really simplify your design and help you get to market quicker and faster. So the one that I'm going to drop in first is this USB-C power and reset module, and it does exactly what it sounds like. And you could see in here, here's the symbol, footprint, and then all of the information about that module, and a reference application on how to wire it up. And then, of course, also the source, and there's release notes, and then there's source in here for all of the design files and whatnot. So I'm going to go back over to my library, and I'm going to look for my USB-C. And you'll find this, when you're doing this, it'll be under user contributed, but if you search for Meadow USB-C, you'll find it. So I'm going to place that up here. All right, so I got my core compute module, I got my USB-C thing, and now I want to add my SCD40 CO2 sensor. And again, looks like I actually made this. There's other ones out there as well. And the quality varies from between them. Like that's a really weird symbol, that one, and that one is probably a module. That's what it says, actually, module, and that's a kind of a wonky symbol. So here's the one I made, and I'm gonna drop that in. And so this is cool. I got my main components, and now I need to figure out like how to start wiring these things up. And this is where data sheets really are your friend when you're doing schematic design. So when you're doing PCB stuff. So if I go over here, here's this is the data sheet for the SCD40 CO2 sensor. And almost every data sheet will have some sort of reference application where it shows how to wire it up. And in this case, this particular one is very simple. It's an I2C peripheral, so it's got clock and data. It's got the pull-up resistors, which we'll talk about in a moment, and then it's got its VDD, which is your power, and then ground. And I think this one also generally needs some power decoupling caps. It's probably somewhere in here. I remember reading about this, about the power requirements. Oftentimes what you do is you put capacitors at the power source, and we'll talk about why and as we actually start to wire that up. But the other thing is that for Meadow designs, one of the best, we also have, there's a data sheet for our parts as well for the F7, and you can find that in the developer portal under Meadow, and then Meadow hardware, and then I think the first link here is the data sheet, and then you'll see hardware designs repo. One of the things that is super helpful for doing Meadow designs with the core compute module is our developer breakout board that you can buy in the store. So this thing here is fully open source, and you can see all of the wiring in the schematic design here, so you can see how things are wired up and whatnot, and that shows a number of the add-on modules, including the Ethernet, SD card, and then the USB-C boot reset one, as well as how to wire up the Core-Compute module itself. So let's start in here. I want to start wiring up my Core-Compute module. So I'm going to zoom in, and let me do a little cleanup here. So the first thing is that this is going to need power, and the way I get power on this is going to be through this USB-C power boot reset module. Basically, 5 volts comes in, and then it provides a nice 3.3 volt out. And again, you can see that in the documentation for that module. So it provides up to 2 amps of 3.3 volt power. So we're going to, let's just move this a little over, and let's start getting this together. Now, I just pulled from here, this is the wiring tools, this is VCC, that's power. And instead of VCC, I like to, there can be lots of different power domains. Like there might be 5 volt, there might be 3 volt. So I like to actually, name it specifically what the voltage is. And 3V3 is a nomenclature to, if you put the V in the middle of that, stands for the point. So instead of 3.3 volt, you can just do 3V3. Likewise, 1.8 volt can be 1V8. So that's a pretty common thing. So I'm going to put 3V3. And the one thing I'm going to change here is my alt snap. And basically, if I start to move this around, it doesn't really line up very good because my snap is too big. So if I change my alt snap, when I hold down alt and then move stuff around, the snap is a little better. So I hit W or grab this wiring tool, and I'm going to hook up the 3V3 rail. And then we've got all these grounds, so I'm going to grab this ground symbol. And I'm going to put this down, kind of down below. And then I'm going to start to wire these up. I hit W. Boop. Boop. All right, and then the same thing over here, except I don't actually need the 5 volt rail on this. I'm not going to use 5 volts anywhere here. And I'm also going to, let's get this shortened. It's just too big out here, right? So we're just going to say USB-C. Add on. Boop, done. So we're going to drop in another ground over here on this side. Start to wire that up. And then since I'm not going to actually use this 5 volt rail, what I'm going to do is say that these are a no connect. So I'm going to put this no connect flag on here. And even though it's a common tool, there's no shortcut to get to it, which is a bummer. All right, so now I have power coming out of this. So I want to power my Core-Compute module. And we'll come back to these connections in a second. But let's go in and create our 3V3 here. And a note about naming. So anytime I name something, that becomes the net name. And then those are connected. So instead of grabbing grabbing a wire and then dragging it over here like that, you could imagine that would become pretty messy. Like pretty quickly, your drawing would be kind of a mess. As long as they have the same name, then the editor will know that they should be connected when the PCB design time comes. All right, so there we go. And then this is a low voltage battery, a 1.8 volt, and that's in the data sheet. We don't want to actually wire that up. So we got that, and then while I'm at it, I'm gonna wire up the ground, and also this this is a little bit small, so I'm gonna make this a little bit bigger. Maybe I'll make it, there we go. That's a little better. Oops. And I like to put my Meadow right in the center because that's usually the main thing. So let's wire up the ground on this one. And there are a lot of grounds. Okay, and now we need to wire up, let's wire up the rest of this USB module. And so to figure out how to wire this up, the thing, like I said, that I like to do is I like to go over here and look at the this is the cheat sheet. You can also, in the add-on modules itself, it'll tell you exactly what each one of those things are and where they should go. There's also a reference application in here showing you that wire up. So this one has more stuff. So we have, if we look at the reference here, we've got VBus, and that looks like it goes to VBus over here on the Core-Compute module. F7 reset, which is the reset button, and that goes over to the Core-Compute module there. And then USB data, positive and negative, those are a differential pair, and we'll talk about it in a second. And then there's the F7 boot. So why don't we wire these up? So let's do first, and this is a this is a net port, so it's basically it's no different than just like naming, like this is a net, this is just another way to provide a named termination. So VBus, 3V 3 enable, that's as if you wanted to have a switch on here that basically turns on and off the power. This will turn off the 3V 3 out, which will basically turn your board off, and we don't need that, so we're just going to put a no connect on there, and then we want our F7 reset, F7 reset, and then we'll need a ground, so we'll do that in a sec. Let's do our USBs, USB DP, right, USB DN, our boot, F7 boot. All right, and then we've got our 3V 3 power. So we're gonna grab this, copy it, put it over here. And I like symmetry, so you'll often see my designs look a lot, left and right the same. Cool. And then these ground, we're just gonna run this through over to here and this to there. All right, so now let's wire these up to the Core-Compute module. So we'll copy them, paste them, boop, boot, and reset. And then it's good practice just to pull them out and show this connection. DN DP, the differential pairs for the USB line, and then the V bus. All right, so that's so far so good. We're going to save this. We now basically have our Meadow hooked up. One more thing that we want to do is if we had any analog input, we would want to provide a voltage reference for that. And we're just going to put one in anyway. We won't actually put an analog on this, but I will put a voltage reference. That's basically saying, hey, you know, if you have analog input signal, what do you want the max value to be measured against? So like, what is the max value that you expect for an input signal? And that, like, in case you had all your analog inputs were 1.8 volts, then you wouldn't necessarily put a 3 volt 3 reference, you'd put a 1.8 voltage reference. But in this case, we'll just do 3 volt 3. All right, so that looks pretty good. So the next thing that we want to do is we want to wire up the I2C for this SCD, this SCD40. And I'm going to actually hit space, and I'm going to rotate it. There we go. So now it's I2C is on the right, and then got more ground and power on the left, and then do DNC, which is do not connect. You can also, there's a tool up here, you can mirror it for whatever reason. If we wanted to put those, you know, we wanted to put the net ports on the left side, we could. And that can be useful in keeping your drawing clean, but it won't affect the, you know, whether you mirror it or not, the PCB design will be the same. All right, so SCDA is SDA, serial data. So this is going to be I2C data, and then we're going to do, all right, I2C and clock. As those, pull them out. Okay, and then we're going to put a no connect flag on all these. Do not connects. And we're going to hook up ground. Boop. And then VDD, which again is our power. So we're going to grab our 3 volt 3, copy, and put that in here. Boop. Another one over here. And VDDH. And if we were to go to the data sheet, we'll see that, you know, oftentimes you'll see two VDD. You'll see like VDD and VDD IO. And oftentimes peripherals will have two voltage domains. Maybe it'll be the voltage domain of the signal of the logic. Like if you're on an Arduino, you might have a 5 volt voltage for the signal for the communication bus, because Arduino, a lot of them are 5 volt. But like the actual chip runs on 3.3 volts, right? So in our case, they're going to be the same, both VDD and VDDH. So supply voltage IR source must be connected to VDD on a customer PCB. So in this case, I think this sensor is like a 3 volt 3 sensor. Oh, actually, you can power it by 5 volts as well, it looks like. So you can read, you know, as I said, data sheets are your friend. Another thing that I want to talk about actually is oftentimes when you prototype, it's really helpful to start with pre-built modules. And so like with the project lab board, oftentimes we start with this and then we plug stuff in to one of these connectors. Like, you know, this is an I2C. This STEMMA QT is an I2C connector. And so you can just plug in an SCD 40 module from Adafruit, and it has those I2C connectors. And so when you start with these pre-built modules, it's really a great way to speed up your prototyping, because you know that these have already been tested and whatnot. Also, what's great about this is most of these are going to be open source, and so you can go and see the design. So if we go to here, go to technical details, there should be a link to their the circuit design of this. It's in their GitHub repo. Sometimes it can be a little bit hard to find, but they're super helpful because it will show you how they've wired this up. And let's see, where is it out on this? Downloads. Here we go. So here's their version of this, and so you can click on this, and then you can get it. You can get. Let's make this big. That's not big enough. Let's make it really big, and then we can zoom in and stuff. So here's how they've wired it up. So this is the this is the sensor. This the SCD40, or in this case the 41. And what they've done here, they've done a couple of things. Their sensor allows you to do, their board allows you to connect via either 5 volt or 3.3 volt. So they've got some stuff to help out with that. They have this power supply which outputs 3.3 volts if you're powering the board with 5 volts. And then they've got a level shifter here, so that you can actually talk to this board over 5 volts. We don't have to worry about that. Ours is simpler. One thing that they've done here, and this is really common, is there's these two capacitors that are hooked to the power. And I didn't actually see anything in here about normally you'll see in a data sheet for one of these peripherals, you'll actually see the power will have capacitors connected to it, and a capacitor is basically like a fast acting battery. It's not quite, doesn't have the energy density, but it works very fast, and the reason why they put these capacitors in there, these are called power filtering. And because these digital peripherals really like a constant, uninterrupted signal of 5 volts or 3.3 volts, then these batteries, if other things turn on and use the power for for a moment, then these capacitors will fill in any dropouts in the power. And they've got a 10 microfarad and a 0.1 microfarad capacitor to do this, and basically the smaller capacitor here works faster, so higher frequency, and then the larger capacitor can hold more energy but will actually work on a slower frequency. So this is a great design. This is really common to have a 10 microfarad and a 0.1 microfarad capacitor. You could arguably on something like this you just use a couple of 0.1s, but we'll actually follow this design because I think it's good. So we'll do a 10 microfarad and a 0.1 microfarad for that power filtering. And for what we call jelly bean components like resistors and capacitors, those we're going to find over here under the common library. And if you look at one of these, so this is a capacitor 0603 US, and there's different sizes here, 0603, 0201, 0402. And those numbers refer to the size. And we generally recommend when you're designing hardware to be assembled at home, don't use anything smaller than an 0603. We can actually go in here in our docs here, and you see under under component sizes, here's actually the sizes. And these are imperial. 0603 is an imperial size, and that size there, this is real size. You don't really want to use anything smaller than that, because anything smaller than that is just too difficult to place. In production designs, oftentimes you'll use an 0201. So for instance, if you have a Meadow F7 board and you pick it up and take a look at it, the components that are on there, the little tiny components around the chips, those are capacitors. They're doing the same thing that we're going to do with our design, which is power filtering, and they're just very, very, very tiny. They're 0201, and they either need to be placed with a robot or they need to be placed under a microscope. So we don't want that nonsense. We want to make these at home. So 0603 is about the smallest we're going to go. So we're going to grab an 0603 and put this one, and then we're going to do this one, C1 and C2. Boop, boop. And this is going to be a 0.1, and the other one was a 10, right? Let me see. Let me show the Adafruit. Yeah, 10 microfarad. So we're going to 0.1 microfarad, and this one's going to be a 10 microfarad. Okay, so we've dropped them in, but they don't actually have any part numbers. Whereas like when we drop this in, it's got a part number, and we dropped in this, it's got, well, no part number on that one, but you know what that one is. So we need to go find some parts for this. So what I do is I go to, there's a couple of really great websites, Octopart and also OEM Secrets. These are two fantastic websites. And I can just go in here and I want to say 0603 0.1 microfarad capacitor. And this will give you just a pile of options for a 0.1 microfarad, also known as 100 nanofarads. And it'll give you, this is really fantastic because it tells you how many are on the market, so their availability. You want to generally buy stuff that has a lot of availability. You want something that whose life cycle is generally in production, they're not end of life. It's also good to know that these Jelly Bean parts are interchangeable. So a Kemet, a Kyocera, AVX, you know, as long as it's an 0603, it's going to be good. And with capacitors, the rule of thumb is that your voltage rating should be double what the working voltage is. So in this case, it's a 3-volt 3 capacitor. So 10 volts, great. 6 volt is a little on the low side, but 10 volt is perfect. And we've also sort of standardized on Yageo. So what happens is that as you start to build stuff, you'll have kind of a library of parts, and you'll have maybe a shelf or a box full of parts. You'll buy these. These are very cheap. You know, they're like a penny each. Some of these are less than a penny each. And so you buy a whole reel of them, and it's like a lifetime supply. There's like 15,000 in a reel, and it might be $10 or $15. And basically by standardizing on different brands, then that helps you sort of like manage your library. So here are 0603, 0.1 microfarad, Yageo cap. I don't need a 50 volt. I can probably, 10 volt, 16 volts, totally fine. It doesn't really matter. Once you go over that, it doesn't really matter. So I am going to, this one looks like, so it's an 0603, and there's 230 million of these on the market. So that's pretty easy one to come by. There's also this one. It's the difference here, a cent and a half versus a cent. It doesn't really matter. So I'm going to come in here. I'm going to grab this part number. You can see that they're very easy to get. All of the major suppliers have lots of them. So that was the 0.1 microfarad capacitor. So I put in the part number. I put in Yageo. And now let's go back to this, and we need a Yageo 0603 10 microfarad capacitor. And here we are again, 0603, 6 million of those. There's 10 million of these, and they're all basically the same. So that one's a 6.3 volts. So that's a little bit low, but this 16 volt is good. If we look at some of the other ones, 10 volt, that's good, and there's a ton of those. That's 10 microfarad. So this one's fine. This one's 8 cents, which is pretty expensive. I'm not sure why, but this one is like half a cent, and there's a gazillion of them on the market. Real tight tolerance, 1% within tolerance. So I'm going to grab this one. Oh, you know what? This is, yeah, that's a resistor. Look at that. I noticed because it was RC. I wonder why it showed me a resistor rather than capacitor. Anyway, we don't want that. So, let's do this one. Nope, 6.3 volts. Here's one. 3 million of them on the market. 10 volt. Good. Good enough. And really what you'd be doing on your own designs is over time, you're going to have these designs built up, and so you're probably going to go and find another design that has that you've already done that has that part. And this is also something that I highly recommend is to go and look at our designs as well. So here's the Klima design, and you can actually find this in the Klima repo under source, and somewhere, maybe it's under documents. Anyway, there's somewhere in here is the design for this, and you can find all of the schematics and whatnot somewhere in here. In any case, here it is in Easy EDA, and here is the design that I had from before. And in this design, I used a 0.1 microfarad on both of them. And then what I would ordinarily do if I were doing a new design, I would just grab this. I would grab this whole thing, and I would copy and paste. And I highly recommend that you do the same in your own designs. Just, most of these IoT designs are just modifications of stuff that are kind of the same thing over and over. So go open up the Klima source, and just if you want a CO2 sensor, just grab that part of it and toss it in. All right, so we've got our two capacitors, and the way that you wire capacitors is you wire them between power and ground, because again, they're like a battery. So we're going to put this here, and I'm going to put this one on this side because you generally want them balanced. These are going to be connected internally, so it's fine if they were, on different sides. But so VDDH, VDD. Cool. So that is wired up. And then if we go back to our data sheet for this, you'll also notice these two resistors. And these are pull-up resistors on the I2C line. And here it is. It says both SCL and data lines should be connected to external pull-up resistors, e.g. RP of 10K, to avoid signal contention. Sorry, that's the next sentence. To avoid signal contention and blah blah blah. These are pull-up resistors, and what a resistor does is it allows a kind of a trickle of electricity to come through by slowing down the electrical pathway. And you can read all about pull-up resistors in our electronics tutorial here. There's pull-up and pull-down resistors. And basically what pull-up resistors and pull-down resistors do is they provide a default value. Because if you have something like this line is basically, this input line is floating. So here's a button, and then on the other side is power. This input line, because it's not pulled up or pulled down, can be indeterminate. It's basically floating. There's a little piece of wire here, and that can act as an antenna, and it can pick up stray electromagnetic interference. And what we do is by allowing a little bit of a trickle through a resistor, we provide a default value. And because we put a big resistor in there, it only allows a little bit of electricity, so that when this comes through, this is a lot of electricity, then it overrides this value. And so there's a pull down resistor, and here's a pull up resistor. And typically on I2C lines, you do exactly that. You have a pull up resistor, which provide default value. And typical pull-up resistors are for I2C are 4.7K, but it doesn't 4.7 thousand ohms. But it doesn't have to be. And it says here that in practice, most will work reliably with a couple of 4.7K resistors. You can actually modify that if you got a lot of devices on your bus. You might have higher pull-up values, but generally start with 4.7K, and that will be just fine. So we're gonna add those. So we're gonna pull out these, and we're going to put 3.3 here, and then let's move this up. Boop. All right. We're going to put a pull-up resistor circuit right below it. And we're going to go back over to trusty Octopart or OEM secrets, up to you. And we're going to say, all right, so we need 0603, 4.7K Yageo. And we want them pretty accurate. We're going to say 1% tolerance. So here we are, 0603, and resistance. Ooh, this one looks good because there's like a gazillion of them on the market, but look, they're 47.5K. And I actually made this mistake quite a bit. Or this one's 4.7. Yeah, that's right. Sometimes it'll be like 4.7, not 4.7K. So 4.7K, 5 million of these, 4.7K, 290 million of these. So that's like a pretty common one. 340 million of those, and these are basically the same. Oh, they are the same. Look, they're the same. Okay, 7L, 7KL. I don't know what the difference is between these. Probably doesn't matter. I'm going to pick this one just because there's like even more. 340 million of them in the world. Oh, that's 47K. That's wrong. We don't want that. That's what the difference between them were. 4.7 and 47K. Look at that. That's what the swap there. So here we are. RRC0603FR 074K7L. So we're going to go to the commonly library, aka common. By the way, in here there's US, and then, it looks like, and then over here the EU symbols. You can use either one. I like these ones better. They just look clearer to me. So this is going to be a 4.7K resistor. And let's put our part number in. Yageo. All right. Make this a little bit more compact. We're going to make 2 of these. Boop. All right. So this one, clock. This one goes to data, and then they both get pulled up. Cool. So there's our pull-up resistors. And what's cool is now we can go up and we can see all our parts. If we go to fabrication and we see BOM, there's all our parts that we need. And if you assign LC, SC parts to these, you can also get a price out of here. But another thing that's cool, we can export this BOM. And then, so now that it's exported, let's go over to where we exported this to. And this is a little, there's kind of a, there's a bug in this, but if you go to Octopart and you go to the BOM tool, this is really cool. You can upload your BOM. So in order to do that, though, we have to go. So here we are, BOM. Which was this? This is going to be dev camp. There should be a dev camp. We just exported it, right? Let's try it again. BOM. Where did we export? Export. Oh, I put it in the wrong spot. Here we go. Oops. All right. All right, we got it. It's exported. Okay, so BOM and dev camp. So for some reason, there's a bug in the Octopart thing. The BOM that you export from EasyEDA won't open, but if you open it up in Excel or Numbers and then re-export it as a CSV, it cleans it up. So we're just export, replace, and then if we go back over to Octopart and then you upload the BOM, you can see, it'll take a moment, it'll price everything out, and it's pretty cool because you can, there it is, takes a moment. Oh, and they come in and there's multiple matches, so we just have to choose the one that's right. And it's usually the first one, and it's pretty easy to see. Boop. And then you can add other stuff too, like it missed the ones that weren't the Meadow parts because the Meadow parts didn't have a part number. And then you can see, so if you make one of these, it's like $30, but if you make 1,000 of them, they go down to $20. And it's cool. You can see like places that you can buy them and the prices and all that. So BOM tools, pretty nice. So we actually have the BOM for all of our different parts and whatnot are in here. So here's Fuego, and this is minus the Meadow parts, but you can see that 250 of them, they're like $10 in parts, and then you add the Meadow bits in and stuff. So that's a pretty cool thing, the BOM tool. Okay, so we're basically design complete. We want to do one other thing, which is we want to grab an RGB LED, and I want that so that we can do some like nice just debug stuff. It's nice to have an LED on your board. So I'm going to grab that from a previous design. I'm going to pull that, like I mentioned, this is something we do, just grab from another design. I'm going to grab that from Klima. So I'm going to grab this RGB LED here. Where did it go? There. Where did my file go? Did I move it around accidentally? Yeah, here we go. So I'll put this over here. And then we're going to wire them up, RGB, LED. And you can see in Klima, we're wired up over here, D9 through 11. So I'm lazy. So I'm going to grab it and plop it in to here. Boop. And then you'll see in Klima, one thing that I like to do is I like to keep track of all of our PWMs and interrupts and stuff, right? Because interrupts can't share the same interrupt channel. Otherwise, the MCU cannot distinguish which one it came in on. So if you put an interrupt on PF8 and PC8, for example, and the number there is the interrupt channel, then it won't know which one is the interrupt was triggered on. So what you would do is use one for like a digital output and the other one for interrupt stuff. So you just keep track of your stuff. And so I'm going to grab these PWM timers. I'm just going to put those in. Wait, that's not the right. This is the one. PWM timers. So we're just going to track that here. Cool. So this is basically complete. And now I mentioned earlier there's this design manager, and this is really cool. So now this is going to validate my design. And if I go over here in Nets and I refresh it, it's going to say, hey, listen, you haven't terminated this. It's an incomplete net. It's like, oh yeah, so we have to go in and we have to terminate all these ones that we're not using. So just got to come in and click the X, the no connect. Be cool if we could just drag and no connect all of these. There's a lot of I/O on this module. It's so powerful. Oops, missed it. Boop. Yeah, I love designing stuff with it because there is so many things that you can put on it. Oh, missed again. All right, delete that. Cool. So now let's save this, and when we refresh our nets, they're good to go. All right, all right. So I think, look at my notes. I think that is everything we want to, everything we want to cover in this first talk. So next up, we're going to take this schematic design and we're actually going to turn it into a PCB design. So that'll be really fun. So that'll be up next. So thank you for joining me on this one. And I look forward to seeing you in the next one. All right.